Okay, it's time for Lesson 11 in our examination of the application layer, part of our course, Networks and Distributed Systems, based on the text Computer Networking, a Top-Down Approach by Jim Couros and Keith Ross. Let's proceed. The applications we have discussed in this unit so far, including the web, email, and DNS, all user client-server architectures with significant reliance on always-on infrastructure servers. Peer-to-peer architecture, on the other hand, requires minimal or no reliance on always-on infrastructure servers. Instead, pairs of intermittently connected hosts, called peers, communicate directly with each other. The peers are not owned by a service provider, but are instead desktops and laptops controlled by users just like you. In this lesson, we'll examine two different applications that are particularly well suited for peer-to-peer design. The first is file distribution, where the application distributes the file from a single source to many peers. The second peer-to-peer application we'll examine is a database distributed over a large community of peers. In client-server file distribution, the server must send a copy of the file to each of the peers, which places enormous burden on the server and consumes a large amount of server bandwidth. In peer-to-peer file distribution, each peer can redistribute any portion of the file it has received to any other peers, thereby assisting the server in the distribution process. One of the more popular peer-to-peer file distribution protocols is BitTorrent. Originally developed by Bram Cohen, there are now many different independent BitTorrent clients conforming to the BitTorrent protocol, just as there are many web browser clients conforming to the HTTP protocol. In this lesson, we first examined the self-scalability of peer-to-peer architectures in the context of file distribution. We then described BitTorrent in some detail, highlighting its important characteristics and features. To compare client-server architectures with peer-to-peer architectures and illustrate the inherent self-scalability of peer-to-peer, we now consider a simple quantitative model for distributing a file to a fixed set of peers for both architectural types. As shown here, the server and the peers are connected to the internet with access links. We make the simplifying and generally accurate assumption that the internet core has abundant bandwidth, implying that all the bottlenecks are in the access networks. We also suppose that the client and the server are not participating in any other network applications, so that all their upload and download access bandwidth can be fully devoted to distributing this file. However, upload and download time is a limited resource. In the client service architecture, none of the peers aids in distributing the file. The server must transmit one copy of the file to each of the peers. Thus, the server must transmit a lot of bits. The number of bits in the file times the number of peers, to be precise. In a client distribution arrangement, the distribution time increases linearly with the number of peers. So, for example, if the number of peers from one week to the next increases 1,000-fold, from 1,000 to 1,000,000, the time required to distribute the file to all peers increases by 1,000. In other words, we're working that server a lot. Let's now go through a similar analysis of the peer-to-peer architecture, where each peer can assist the servant in distributing the file. When a peer receives some file data, it can use its own upload capacity to redistribute the data to other peers. Calculating the distribution time for peer-to-peer architecture is much more complicated than for client-server architecture, since the distribution time depends on how each peer distributes portions of the file to other peers. Nevertheless, a simple expression for the minimal distribution time can be obtained. At the beginning of the distribution, only the server has the file. To get this file into the community of peers, the server must send each bit of the file at least once into its access link. Thus, the minimum distribution time is at least the number of bits in the file. Unlike the client-server scheme, the number of bits sent once by the server may not have to be sent by the server again, as the peers may redistribute the bits among themselves. As with the client-server architecture, the peer with the lowest download rate cannot obtain all the bits of the file as quickly as some of the other peers. However, the impact this has to the transfer is between that slower host and the host sending the file only. We see that for the client-server architecture, the distribution time increases linearly and without bound as the number of peers increase. However, for the peer-to-peer architecture, the minimal distribution time is always less than the distribution time of the client-server architecture. If the download time for the slowest peer is 1 hour, for example, then the download time is also less than 1 hour for any number of peers. Therefore, applications with peer-to-peer architecture can be self-scaling. This scalability is a direct consequence of peers being redistributors as well as consumers of bits. BitTorrent is a popular peer-to-peer protocol for file distribution. In BitTorrent lingo, the collection of all peers participating in the distribution of a file is called a torrent. Peers in a torrent download equal-sized chunks of the file from one another with typical chunk size of 256 kilobytes. When a peer first joins a BitTorrent, it has no chunks. Over time, it accumulates more and more chunks. While it downloads chunks, it also uploads chunks. Once a peer has acquired the entire file, it may leave the torrent or remain in the torrent and continue to upload chunks to other peers. Also, any peer may leave the torrent at any time with only a subset of the chunks and later rejoin the torrent. Each torrent has an infrastructure node called a tracker. When a peer joins a torrent, it registers itself with the tracker and periodically informs the tracker that it is still in the torrent. In this manner, the tracker keeps track of the peers that are participating in the torrent. A given torrent may have fewer than 10 or more than 1,000 peers participating at any instant of time. At any time, each peer will have a subset of chunks from the file, with different peers having different subsets. Periodically, a user will ask each of the neighboring peers for the list of the chunks they have. The user will eventually receive a list from all of the neighboring peers. With this knowledge, the peer will issue requests over the TCP connections for chunks he or she currently does not have. Let's stop here Review your notes and your study guide. Take care of any assignments you may have. And when you return, we will pick up with lesson 12.